Our mission for today is just one word. Clarity?
Clarity. I like.
We are going to speak slowly. We're going to use simple English. And most importantly, we are not going to summarize. We are not going to skip anything.
We are going to take a very complex topic, CPU architecture and the Rust programming language, and we are just going to break it down piece by piece.
One step at a time.
We want to make sure that you, listening right now, understand every single step of the way.
So if you've ever felt confused by how a computer really works, deep down inside the chip, this is the day it's all going to make sense. We've got plenty of time. We're going to explore this together.
By the end of this deep dive, I really want you to be able to close your eyes and just see it, physically see what is happening inside your computer.
Okay. So let's unpack this. What is our main topic for today?
Today, we're talking about functions and directives. But, if we want to give it a more exciting title,
Let's do it.
the mission today is controlling the CPU.
Controlling the computer's brain.
Exactly, the CPU, the central processing unit. It's the brain of your computer, and we want to understand how to control how it thinks and how it moves.
And you mentioned there's a conflict today.
A battle.
There is a battle, a big one.
A battle between who or what?
It's a battle between clean code and speed.
On one side, you have the desire to write code that looks nice, that's organized, that uses functions. It's easy for a human to read.
Right. The good habits they teach you in school.
Yes. But on the other side, we have the need for that code to run fast. Very, very fast.
And usually people think those two things are the same. If I write good, clean code, it should be fast.
Yeah. That is what we're all taught. It makes sense. But in the real world, the world of the physical hardware, it's not always true.
So being organized can actually make the computer slower.
Sometimes, yes. And that's the mystery we're going to solve today. We're going to look at one specific command. It's called inline.
Inline.
Inline. It's a very powerful tool. You can almost think of it like a copy-paste button that you give to the compiler.
Okay, copy-paste, buddy. But you said before we get to the solution, we have to understand the problem.
We have to. Deeply.
So here's the big question for you, the listener. Why does simply calling a function, just telling the computer, hey, go do this one small task, why does that sometimes waste 95% of the computer's time?
It just sounds impossible, doesn't it? These machines do billions of things every single second. But we're going to see how a simple movement in memory, a tiny little jump, can absolutely destroy your performance.
Okay, I'm ready. Let's start at the very, very beginning. We need to look at our example. We have a piece of code here from the source material. It's written in the Rust programming language.
And Rust is a very, very popular language for what we call systems programming.
So things like game engines.
Game engines, operating systems, web browsers, the really low-level fast stuff.
Okay. I'm going to read the line of code now. It might sound a bit technical, but please do not worry. We promise we will explain every single word.
Everyone.
Here's the code. Pub fn new x f32 y f32 z f32 w f32 self.
Okay. Let's take that apart, word by word.
First word, pub, P-U-B.
So pub is just short for public. In programming, you have things that are private, only that one file can see them, and you have things that are public.
Open to the world.
Exactly. Pub just means, hey, everyone can use this.
Simple enough. The next word is fn.
fn is just short for function. It's a signal to the computer. It says, I am about to define a new action, a new verb.
And the name of this new action is the next word, new.
New, yes. And in this specific context, this function is what we call a constructor.
A constructor? That sounds like a construction worker. Someone who, builds buildings.
That is a perfect analogy, yes.
Yeah.
A constructor in code is a special tool that builds a new object. It takes raw materials and it builds a structure from them.
So in this case, what structure is it building?
It's building a vector. To be specific, a four-dimensional vector. You see these in video games all the time.
Okay.
It can represent a position in space, like where a character is standing, or it could be a color.
Yeah.
Or a direction something is moving.
Got it. So we have a builder, the constructor. And a builder needs raw materials to do the work. What are the materials here?
The materials are the inputs, the things inside the parentheses. We have X, Y, Z, and W.
And right next to them it says F32. What does that part mean?
So F32 stands for float 32. A float is just short for a floating point number.
Okay. And in simple English, that means?
It just means a number with a decimal point, like 1.5 or 3.14, or maybe a negative number like -0.01.
Got it. And the 32.
That just tells us how much memory it takes up. 32 bits. It's a very standard size for a number in most video games.
Okay, so let me try to summarize the goal here. We have 4 separate numbers, X, Y, Z, and W. And our job is to bundle them all together into one single object.
Correct. We want to pack them up.
That seems really simple. Why do we need a whole deep dive to explain packing 4 numbers?
Well, to a beginner, it is simple. You just write the code and it works. But we're not beginners today. Today, we are systems engineers. And as systems engineers, we need to look at the physical reality of what the computer is doing. We call this the data packing reality.
Data packing. I like that term. It sounds like we're getting ready for a trip.
We are. We're going on a trip. And I want you to imagine the inside of your computer. When this program starts to run, those 4 numbers, X, Y, Z, and W, they are not sitting together nicely. They are scattered.
Scattered, you mean they're in completely different places?
Yes. Physically far apart inside the computer's memory. One might be in a place called a general purpose register. Another might be on something called the stack. They're all over.
Let's use an analogy here. I love analogies. They really help me visualize things.
Great.
Let's imagine I'm in my house, and I have 4 books.
Okay. You have 4 books. Let's call them Book X, Book Y, Book Z, and Book W.
And I need to go on a trip, so I need to pack these books. Are they all sitting neatly on my bookshelf?
No, that would be too easy, of course. Book X is on the kitchen table. Book Y is hidden under the sofa in the living room. Book Z is upstairs in the bedroom. And Book W is in the hallway, right by the front door.
So they're all over the place.
Exactly. They are scattered.
And the function, this new function we're talking about, what is its job in this analogy?
The function is like you. Its job is to run around the house. It has to go to the kitchen, grab Book X, then run over to the sofa, grab Book Y, then run all the way upstairs for Book Z, then grab Book W.
Okay. I've gathered all 4 books. Now what?
Now it has to pack them all tightly into one single suitcase.
One suitcase.
Yes. And in our computer code, that suitcase has a very specific technical name. It is called an XMM register.
XMM register. Okay. I want to pause here for a second because the source material and a lot of textbooks mention that this part causes a lot of confusion.
Oh, yes.
The source mentions the name XMN0.
Ah, XMN0, yes. This is famous for confusing students. It creates a kind of identity crisis.
Why is it so confusing?
Well, look at the name very carefully. XM0. It starts with the letter X.
Right, and one of our inputs is also called X.
Exactly. So a student sees XMN0 and they immediately think, oh, that must be the special place where the X coordinate goes.
That seems logical. X goes in X.
It does. Or they see the 0 at the end of the name and they think, oh, maybe this is for the coordinate 0.
Is that true? Is that what it means?
No. It is completely wrong. And if you think that, you will completely misunderstand how the hardware actually works. So we need to clear this up right now.
Okay, please explain. What is XMM0?
XMN0 is the name of the locker.
The locker. Like a locker at a gym or at a school.
Exactly like a gym locker. I want you to imagine you walk into a locker room. There's a whole row of metal lockers, and they're numbered. You have locker #0, locker #1, locker #2, locker #3, and so on.
Okay. I can see the lockers.
XMN0 is just the label, the number painted on the door of the very first locker. It just means locker number 0.
And does the label on the door tell you what's supposed to be inside?
No, not at all. The locker is just a metal box. It does not care what you put inside it. You can put gym clothes in it, you can put books in it, you can put 4 bananas in it. The locker doesn't care.
So XMN0 is just the container.
It is the container. In technical language, we'd say it's a 128-bit wide box. It's a box that is just big enough to hold exactly 4 of our F32 numbers.
Okay, let's go back to my books then. I have run all around the house. I have gathered Book X, Book Y, Book Z, and Book W.
Correct. And you take all 4 of those books and you shove them all together into locker, #0, into XMM0.
So XM0 holds all 4 of them, not just the X book.
Correct. It holds X, Y, Z, and W, all of them, packed together, side by side.
That is a very, very important distinction. XMN0 is the bucket. The variables are the water we pour into the bucket.
Precisely. So to summarize, the function pub_mnew is physically doing this work. Go find the scattered numbers, bring them all to the CPU, and pack them tightly into the locker named XMM0.
Okay. I think I really understand the job now. It's a packing job. But here's the big mystery.
Go.
My computer is incredibly fast. I just bought it. It has a high gigahertz number. It can do billions of operations every single second.
Modern CPUs are absolute speed demons. They are unbelievably fast.
So Why is calling this one little function a problem? Why are we even talking about it? If I tell my computer run this function, shouldn't it just happen instantly? I mean, shouldn't it take basically zero time?
You would think so. It seems like it should. But there is a hidden cost. There is a price you have to pay just to use a function. We call this the call overhead.
Overhead. That's a business term, isn't it?
It is. In business, overhead is all the money you spend that isn't actually making the product. You know, like paying the electricity bill for the office or paying for the janitor. It's necessary work, but it isn't the main job.
So in the computer, the overhead is all the work the computer has to do that isn't actually packing the numbers.
Exactly. The CPU can't just run the function. It has to perform this whole complicated dance just to get to the function and come back. The source material breaks this dance down into 5 distinct steps.
5 steps, just to start one simple function.
Yes, 5 steps. Let's walk through what we'll call the physics of a function call. Step number 1 is the stall.
A stall, like when a car engine just dies.
It's similar. Imagine the CPU is it's running down a highway, processing your code, line after line. Suddenly it sees a new command. Call function.
And what does it do?
It has to stop. It has to slam on the brakes and pause because it doesn't know what code comes next. The next piece of code is somewhere else entirely. It has to switch gears.
Okay, so it pauses, it just freezes. What is step 2?
Step 2 is technically called push IP, but a much better name for it is leaving a breadcrumb.
A breadcrumb, like in the story of Hansel and Gretel.
Exactly like that.
Yeah.
The CPU is about to leave its current location in the code. It's going to go somewhere else in memory to find the function, but it needs to be able to come back later.
Right. When the function is finished, it has to return to the exact spot where it left off.
But how will it remember where it was? The CPU has a very short memory. If it just leaves without writing down its location, it will be lost forever. The program will crash.
So it has to write down the address.
Yes. It takes its current location, the instruction pointer, or IP, which is just the address of the current line of code, and it saves it. It pushes it onto a list called the stack.
So it's like putting a bookmark in a book.
A perfect way to think about it, I was on page 50. It writes that down so it can find its way back, and that action, writing it down, takes time.
Okay. Step 3.
Step 3 is the jump. This is where the CPU literally teleports. It changes its focus from your main program to a completely different part of the computer's memory, the RAM.
So it jumps to the location where the function's code actually lives.
It does. And then step 4 is execute. This is the part we actually wanted. This is where the CPU runs around the house, grabs the books, and packs them into the suitcase.
This is the only part that is actually useful work.
Yes. Out of all these steps, only step 4 is doing what we asked it to do.
Okay, and the final step, step 5.
Step 5 is pop and return. The function is finished. The suitcase is packed. Now the CPU has to go find that breadcrumb it left for itself.
It has to find the bookmark.
It goes to the stack. It reads the note. You are on page 50. It says, okay. It picks up the bookmark, and then it teleports back to the main program to continue where it left off.
Okay, let me repeat this back just to be absolutely sure I have it. It has to pause, save a bookmark, teleport to the function, do the work, find the bookmark, and teleport back.
That is the dance every single time you call a function.
Wow. It sounds like a lot of running around for a very simple job.
It is, but
Yeah.
it gets worse.
It gets worse.
It gets much worse. If that whole dance wasn't bad enough, we have another problem, something called the pipeline crisis.
The pipeline crisis. That sounds very dramatic, like the title of an action movie.
It is dramatic for the computer. You see, modern CPUs are not like us. They don't just do one thing at a time. They work like a factory assembly line.
An assembly line, like
Got
in a factory that builds cars.
Exactly. Imagine a long conveyor belt. At the very start, you have raw metal. At the very end, you have a finished car. And you have different workers at different stations along the belt.
Right.
So one worker is putting on the wheels. At the same time, the next worker down the line is putting on the doors of a different car. And the next worker is painting yet another car. They are all working at the same time on different cars.
That sounds very efficient. You get a new car off the line every few seconds.
It is incredibly efficient. And the CPU does the same thing with your code. It's constantly fetching the next 10 instructions from memory while it's still executing the first one. It's trying to look into the future.
It's looking into the future.
Yes. It's guessing. It's making a prediction. It says, I bet the programmer wants to do the next line of code and the next one and the next one after that. So it starts preparing all of them in advance.
It assumes we're just going to keep driving straight down the road.
Exactly. But then
Yeah.
a function call happens.
The teleportation.
Right. Suddenly, the code says JUMP, go to a completely different address.
What happens to the factory?
Chaos. Absolute panic. The factory manager screams, S-stop-P! We're going the wrong way. We made the wrong prediction.
And what happens to all those cars that were on the assembly line? All those instructions the CPU was preparing?
They're garbage. They're useless now. The CPU has to throw all of them in the trash. This is called a pipeline flush.
A flush, like flushing a toilet.
Yes. It flushes away all that wasted work. It has to stop the conveyor belt, throw away all the half-built cars, and then start the whole assembly line over from scratch at the new location.
That sounds incredibly, incredibly wasteful.
It is. Imagine that factory manager yelling, "Stop making cars, we need to make boats instead." Everything has to be thrown out.
So let's put some numbers to this.
Yeah.
We have the overhead from saving the bookmark, we have the overhead from the teleporting, and we have the waste from the factory stopping. The source material gives us a specific calculation.
It does. And this is what we call the physics engine tragedy.
In a video game, like a shooting game or a racing game, we use these vectors a lot, don't we?
Oh, yes. You might be creating millions of these vectors every single second. Every bullet that flies, every snowflake that falls, every leaf on a tree, it needs a vector.
Okay, so in that context, how long does the actual work take? The packing of the suitcase?
The useful work, the part where we actually pack the 4 numbers into the XMN0 locker, that takes only 1 CPU cycle. It's basically instant.
1 cycle. That is very, very fast.
The commute, the travel, the jump, the stall, the saving of the bookmark, the pipeline flush, the return journey, all of that takes about 20 CPU cycles.
So 1 cycle of useful work and 20 cycles of travel and waste.
Correct. So now we can look at the formula for efficiency. Useful work divided by total time. In this case, that's 1 divided by 21.
1 divided by 21. That's going to be a very small number.
It's about 0.047, or if we think of it as a percentage, it's 4.7%.
Wow. Wait, so only 4.7% of the time is spent doing the actual work?
Mm-hmm.
And 95.3% of the time is spent just moving around.
Exactly. We're spending 95% of our computer's power traveling to the function, and only 5% of the time actually doing the math we wanted to do.
That is unacceptable.
It is completely unacceptable. Imagine if you hired a plumber to fix your sink, and he charged you for 20 hours of driving around and only 1 hour of actually fixing the pipe.
I would be furious.
Yeah.
I would not pay him.
And that is how your CTU feels. It's wasting its life commuting back and forth. It wants to do work, but you're forcing it to drive around all day.
So we have a very clear problem. The function call is way too expensive for these small, fast tasks.
Yeah.
We need a solution.
And we have one. This is where we solve the mystery. The solution is a special command called Inline.
Inline. I see it in the source code here. It looks like this. #inline. Always.
Yes, this is what we call a directive. It's not code that actually runs. It's more like a note, a direct order that you give to the compiler.
And the compiler is the program that translates our human-readable Rust code into the machine language the CPU understands, right?
Exactly. It's the translator. So the inline command is a direct order to that translator.
And what does the order say?
It says, do not make a function call.
But, wait a minute. We wrote a function. We typed mn new. We defined a whole function. How can it not be a function call?
This is the magic. This is why we call it the copy-paste command.
Copy-paste. You mean like in a word processor, like
Well,
Control-C, Control-V.
Exactly like that. When you add #inline, always, the compiler looks at your code. It sees the function new. It looks inside that function, and it sees the instructions. Pack X, Y, Z, and W into the locker.
Okay. It sees the useful work.
And instead of creating a jump command, instead of creating a teleport command, the compiler takes those instructions from inside the function, and it physically copy-pastes them directly into your main program, right where you use the function.
So it deletes the teleportation entirely.
It deletes the teleportation, it deletes the bookmark saving, it deletes the pipeline flush, it deletes the return jump. All of it is gone.
Let's try to visualize this just to make it crystal clear for everyone.
Okay. Let's imagine scenario A. This is without inline, the slow way.
Okay.
The CPU is reading the main code. It says load data. Then it sees the command call function.
So it has to stop. It saves the bookmark.
Yeah.
It does the bookmark.
It travels to the function. It does the work. Then it has to JUMP back. That's the plumber driving for 20 hours.
All right. Got it.
Now, scenario B. This is with inline, the fast way.
Okay.
The CPU is reading the main code, and it says load data. The next line says pack data, and the next line says store data.
There's no jump.
No jump, no pause, no stopping, no breadcrumbs, nothing.
The instructions are just Right there, sitting in the main code.
They are just there. The CPU flows like water. It reads line 1, then line 2, then line 3, then line 4. It never has to look away. It never has to stop the factory. The assembly line keeps moving perfectly.
Just what's the overhead in that case? What's the travel time?
Zero. Zero overhead. The travel time is completely gone.
That is amazing. It really is like a magic trick.
Yeah.
We get the benefit of organizing our code with functions, which makes it easy for us humans to read. But the computer runs it as if we wrote it all in one long, straight line.
Exactly. That is the power of Inline. It is one of the most important tools for a systems engineer. It gives you the best of both worlds. Clean code for you and fast code for the machine.
Okay, so we solved the software problem. We know how to fix the jump. But this deep dive is about to get even deeper, isn't it? We need to look at the hardware again.
Yes. We talked about XMM0, the locker, but why do we use that locker? Why is it that particular size? To understand this, we have to look at the history of the CPU. We need to look at the evolution of registers.
And registers are the lockers inside the CPU.
Correct. They are the super high-speed storage boxes right inside the brain. And over the last 30 years or so, these lockers have been getting bigger and bigger and wider.
Let's walk through the timeline. The source material lists 4 main generations of these lockers.
Okay. First, we have the grandfather, the ancestor. It's called MMX. MMX.
It stands for Multimedia Extensions. This came out in the 1990s. It was 64 bits wide.
64 bits.
It was okay for its time, but it's basically obsolete now. We don't really use it much anymore.
Okay, so goodbye MMX. What came next?
Then came XMM. This is the one we are using today in our example. This technology came with the Pentium III processor way back in 1999.
1999. That's still pretty old.
It is old, but it is the standard. It's the reliable workhorse of the industry. XMM is 128 bits wide.
And 128 bits is exactly enough space for 4 of our 32-bit numbers.
Exactly. 4 times 32 is 128. It is a perfect fit for our vector XYZW.
But technology never stops. They got bigger, right?
Oh, yeah. Next came YMM. This is part of a technology called AVX, and these registers are 256 bits wide, double the size. They can hold 8 numbers at once.
Double the size. That sounds so much better. And what's the biggest one?
The giant. The monster, that's ZMM. This is part of AVX 512. It's 512 bits wide. It can hold 16 numbers at once. 16 numbers. That sounds amazing. So if I can process 16 numbers all at the same time, why would I ever use the small XMM locker that only holds 4?
That is the logical question, isn't it? Bigger is always better, right? If you have a bigger truck, you can carry more cargo. If you have a bigger pipe, more water can flow through.
Usually, yes. That's how it works.
But in hardware, there is always a cost. There is always a price to pay for power. And this cost involves electricity and heat. To understand it, we need to learn about a concept called power gating.
Power gating. Okay, that sounds pretty technical. What is that?
Think of the registers as a layered cake. Or, you know what, an even better way to think about it is nested compartments.
Nested. You mean like those Russian dolls? You know, the wooden dolls where you open one and there's a smaller one inside and a smaller one inside that?
Yes. That is a perfect image. Let's imagine the registers are those Russian dolls.
Okay.
The smallest doll, the one in the very center, that is XMM, the 128-bit part.
Okay, the core.
The medium-sized doll, which surrounds the small one, that's YMM, the 256-bit part.
So it's a layer on top.
And the largest doll, the one on the outside that holds everything, that's CMM, the 512-bit part.
Okay, I can picture that. Layers wrapped around layers.
Now, modern CPUs are completely obsessed with saving power. They want to save your laptop's battery life. They want to stay cool.
Right.
So if your program is only using the small doll, the XMM register, the CPU physically cuts the electricity to all the outer layers.
It just turns them off.
Yes, it turns off the lights. The YMM and ZMM parts of the chip sit cold and idle. They are completely asleep. They use 0 electricity.
That sounds very smart. A great way to save energy.
It is smart, but what happens when you suddenly decide to use a big AVX instruction? What if you write code that needs to use that giant ZMM register?
You have to wake it up.
You have to wake up the giant.
Mm-hmm.
And the CPU has to suddenly pump a huge amount of electricity into those massive outer layers of the doll.
What happens when you do that?
It creates something we call a thermal tax.
A tax, like a penalty or a fine?
Exactly, a penalty. Activating those huge circuits consumes a massive amount of electrical current, and basic physics tells us when you push a lot of current through a tiny wire, it creates a lot of heat.
So the chip gets hot.
Extremely hot, dangerously hot. The temperature spikes almost instantly.
So what does the CPU do to stop itself from melting?
It panics. It has to engage a safety mechanism. This is called frequency downclocking.
Downclocking, that just means slowing down, right?
Yes. To survive the heat, the CPU has to lower its speed, it reduces its gigahertz, it slams on the brakes to cool down.
Can you give me a specific example with numbers?
Sure, let's say your CPU normally runs at a nice, speedy 4.5 gigahertz.
Okay, 4.5.
Then you run a program with a heavy AVX 512 workload. You wake up those giant ZMM registers.
And boom, a massive heat spike.
The CPU detects that heat. It says, whoa, too hot, and it immediately drops its speed all the way down to 3.5 gigahertz, or maybe even 3.0 gigahertz in some cases.
That is a huge drop. That's like losing 30% of your speed in an instant.
It is. And here's the really bad part. It drops the speed for everything.
Everything.
Yes, even the parts of your program that aren't using AVX. Even your operating system. The entire chip slows down just to cool off.
So, by trying to be faster using the big registers, I might actually make my whole game run slower.
Exactly. You tried to be smart, but you ended up making the whole system sluggish and unresponsive.
Done.
This brings us to the sedan versus sports car analogy.
I love car analogies. Let's hear it. Sedan versus sports car.
AVX, the big registers, is like a high-performance sports car, a Ferrari or a Lamborghini.
Super fast.
Extremely fast, top speed. If you are on a long, straight highway with no traffic, it is absolutely incredible.
When are we on a straight highway in computing?
When you're doing something like, say, video encoding, or complex matrix multiplication, or specialized scientific math, you're just doing the same big calculation over and over again for a long time. You just go fast in a straight line.
Okay, so AVX is the sports car. What about SSE? What are the smaller XMM registers we've been talking about?
SSE is like a sedan, a family car, a reliable Toyota Camry.
Okay, reliable.
It doesn't have the highest top speed, it's not as flashy, but it runs cool, it's very efficient, and most importantly, it handles stop-and-go traffic very, very well.
And a game engine. Is that a straight highway? Or is it city traffic?
A game engine is messy city traffic. It's constant stop and go.
Why is that?
Because the game is always doing many different things at once. It does a little bit of physics, then it has to check the AI for the enemies, then it draws a picture on the screen, then it plays a sound effect, then it checks for your controller input. It's constantly switching between all these different small tasks.
So if you tried to use the sports car, the AVX, and all this stop-and-go traffic?
The engine would overheat constantly, the car would have to stop and pull over to cool down every few seconds. You would actually get to your destination much later than the person driving this slow and steady sedan.
That is a brilliant explanation.
Yeah.
So for things like physics engines, we prefer the sedan, the SSE XMM registers, because they are stable. They don't cause the whole CPU to downclock.
Precisely. Stability is often more important than raw peak speed in a complex system like a video game. We want a consistent, predictable speed, not a burst of speed followed by a sudden slowdown.
Okay, so we've learned two huge things so far. Number one, use inline to avoid the cost of jumping for small functions.
Right.
And number two, use the smaller XMM registers to avoid the cost of heat and downclocking.
Correct. Those are the two pillars of our performance strategy.
But I have another question. Let's go back to inline for just a moment.
Okay.
You said inline is like copy-paste. It removes the overhead. It makes the code flow like water.
Yes, it does.
So, if it's so good, why don't we just inline everything? Why don't we take our whole video game, millions of lines of code, and just make it one giant inline function?
The classic question. Why not inline everything? If a little bit of something is good, then a lot must be better, right?
It seems logical. If jumping is bad, let's just never jump.
But in engineering, there is always a trade-off. There is no such thing as a free lunch. The problem with inlining everything is a new problem called code bloat.
Code bloat. That sounds like the code is getting fat.
It is getting fat, yes.
Yeah.
Remember, inline is copy-paste. So imagine you have a function that is, say, 50 lines long, and you call that function 1,000 times in your program.
Okay, 1,000 different places.
If you use a normal function call, the code for that 50-line function exists in one single place in memory. The computer just jumps to that one spot 1,000 times.
That's very efficient in terms of space.
Extremely efficient. But if you inline it, the compiler copy-pastes those 50 lines 1,000 separate times.
Oh. So 50 lines of code becomes 50,000 lines of code.
Exactly. Your final program file becomes huge. This is what we call the memory footprint.
But hard drive space is cheap. My computer has terabytes of space. Why do I care if the final program file is big?
You don't care about the hard drive. You care about the cache. To understand this, we have to talk about the memory hierarchy. We need to talk about where the CPU gets its instructions from. This is the distance problem.
Okay, let's break down the memory hierarchy. This seems like the last big piece of the puzzle.
The CPU is fast, but it is also very hungry. It's starving for data. It needs to eat instructions constantly to keep working. It needs to be fed.
And who feeds it?
Well, there are different kitchens or storage areas it can get food from. The very best one is the L1 cache.
L1, level 1.
I want you to think of the L1 cache as the desk that is right in front of the worker. It's tiny, it can't hold much stuff, maybe just a few sheets of paper, but it gives you instant access.
How fast is it?
It takes roughly 1 cycle to grab something from the desk. It's right there. You don't even have to think about it.
Okay, so we want our code to be on the desk.
Yes, always. But if the desk is full, we have to go somewhere else. We have to go to the warehouse. And the warehouse is the RAM, the main memory.
The RAM sticks that you plug into the motherboard.
Exactly. Think of RAM as a massive, massive warehouse. It can hold everything. It holds gigabytes and gigabytes of data. But it is physically far away from the worker.
How far away?
In computer time, it's an eternity. To fetch data from the L1 desk takes 1 cycle. To fetch data from the RAM warehouse takes around 300 cycles.
300 times slower.
Yes. The electrical signal has to travel through long wires, out of the CPU chip, across the motherboard, find the data in the RAM chip, and then travel all the way back.
It's the difference between reaching for a stapler that's right on your desk versus having to walk out of your office, get in your car, and drive across town to a store to buy a stapler.
That is a perfect analogy. You do not want to be driving across town every time you need a stapler.
So how does this connect back to inline and code bloat?
This is what we call a capacity miss.
A miss?
If your code is small and compact, it fits on the desk. It fits in the L1 cache. The CPU can read all the instructions it needs without ever getting up. It runs incredibly fast.
But if I inline everything?
If you inline everything, your code becomes bloated, it gets fat, it becomes huge, and it physically does not fit on the tiny desk anymore.
So what happens?
The CPU executes the first part of the code from the desk. Then it looks for the next part. It says, oh, it's not on my desk, so it has to stop everything. It has to take a long walk to the warehouse to RAM to get the next chunk of code.
And that walk takes 300 cycles.
Yes. Then it runs that little chunk, and then it has to walk all the way back to the warehouse for the next chunk. It's constantly walking back and forth, back and forth.
So by trying to save the 10 or 20 cycles of jumping to a function,
you created a new, much worse problem that costs 300 cycles every time you need to fetch from RAM.
we made it so much worse. We tried to optimize, but we actually made it much, much slower.
Much, much worse. This is the capacity miss killer. The cost of walking to the warehouse is far, far higher than the cost of a small, predictable jump.
So there must be a golden rule here. When do we inline and when do we not?
The golden rule is actually very simple. It's all about balance.
Tell us the rule. Rule number 1, small functions. I'm talking tiny functions, like our vector construct anew or a simple addition or a dot product. For these, you should always inline.
And why?
Because the code inside them is tiny, maybe just 1 or 2 instructions. The cost of the jump, which is 20 cycles, is huge compared to the work, which is 1 cycle. And copy-pasting 2 lines of code isn't going to cause code bloat. It still fits on the desk.
Okay, that makes perfect sense. And rule number 2?
Rule number 2, large functions, things like load level from disk or connect to game server or other massive blocks of logic. For these, you should never inline.
And why not?
Because the jump cost of 20 cycles is nothing. It's basically free compared to the execution time of the function, which might be millions of cycles. And copying that huge block of code everywhere would destroy your cache. It would force the CPU to live in the warehouse.
So it's all about that balance. Programming is about choosing the right tool for the right job.
Exactly. Sometimes you need the sedan, sometimes you need the sports car, sometimes you do inline, sometimes you call. You have to be smart and think about the hardware. This is absolutely fascinating. We really are controlling the physical behavior of the machine. We're like traffic controllers for data.
We are. We are deciding where the electrons flow inside the chip.
Before we finish up, the source material gives us a couple of deep thinking assignments. These are little thought experiments to test our understanding.
Yes. These are fun. They help us stretch our brains a little bit.
The first one is called the recursive crash.
Ooh. Recursion. That is a scary word for some students.
But recursion is a simple idea, right?
Uh-huh.
It's just when a function calls itself, like a function named A that has a line of code inside it that says run function A.
Right. It just loops on itself.
Now here's the thought experiment. Imagine you have one of these recursive functions, and you tell the compiler to hashtag inline always.
Oh no, that's not good.
What happens?
Okay, think about the copy-paste rule. The compiler sees the call and tries to copy the function's body.
Right.
But inside the body that it just pasted, it sees the function call again. So it says, oh, I need to copy-paste the body here inside the first copy.
And inside that new body.
It sees the call again, and it says, oh, I need to copy-paste it again.
And inside that one.
Copy-paste, and again, and again. It's trying to create an infinite Russian doll.
Does it ever stop?
No. It is an infinite loop of copy-pasting. It never ends.
So what happens to the poor compiler?
Well, a smart compiler will give you an error message. It will say something like, recursion limit reached, and just stop. But if it wasn't smart, it would just keep going until it ran out of memory and crashed. It physically cannot construct the final file because the file would have to be infinitely large.
That is a great mental image, the compiler just trying to type forever and ever.
And the second assignment is called the debugging nightmare.
Debugging is fixing errors in your code.
Yeah.
And usually programmers use a special tool to step into their code one line at a time.
Right. You click a button that says step, and it runs line 1. You click step, it runs line 2. You see a function call, and you can click step into function, and it jumps you to the start of that function.
If we used inline,
remember what we said. The function has been destroyed.
it's just gone?
The structure is gone, the jump is gone, the compiler smashed the code into the main program. It's like the walls of that room have been completely knocked down.
So if I try to step into that function in my debugger, what happens?
You often can't. Or the debugger gets very, very confused. The source code you were looking at on your screen shows a nice, clean function, but the actual machine code that is running in the CPU does not have a function there at all.
So the map doesn't match the territory.
Exactly. The debugger might jump around in a confusing way or just skip over it entirely. It is very, very hard to fix bugs in highly optimized code sometimes.
That's the price we pay for speed.
Indeed. Speed often comes with complexity.
Wow. We have covered a massive amount of ground today. I really think we have fulfilled our mission of clarity. Let's just recap our journey one last time.
We started with that simple FN keyword. We learned that data like X, Y, Z, W is scattered like books all over a house, and we have to pack them into the XMN0 locker.
Then we learned about the call overhead, that whole dance. Pause, push breadcrumb, teleport, return. And we learned how that dance wastes 95% of the computer's time for these small, fast tasks.
We discovered the solution. #inline always. The magical copy-paste command. It lets the CPU flow like water without ever stopping.
Then we took a really hard look at the hardware, the evolution from MMX to ZMM, and that thermal tax. We learned why the bigger registers, the AVX, act like a sports car that overheats in city traffic, making the sedan, the SSE, the better choice for something like a physics engine.
And finally, we discussed the cache. The desk, the L1 versus the warehouse, the RAM. And we learned why inlining everything causes code bloat and forces our poor CPU to take long 300-cycle walks to the warehouse.
It's a complex puzzle. But I hope that now, when you look at code, you don't just see text on a screen. I hope you see the factory.
I hope you can see the assembly line, you can see the lockers, you can feel the heat, you can see the long distance to the warehouse. That is what a systems engineer sees.
And to leave you with something to think about, here's a final provocative thought.
Go on.
Think about your own computer right now. Maybe you're listening to this on a laptop or a desktop, maybe even a phone.
Okay.
Sometimes you hear the fan spin up, you hear that whoosh sound, and the computer gets hot.
Yes, I hear it all the time when I'm working.
Is it possible that it's because a program you're running is using those massive AVX registers? Is your computer slowing itself down? Is it downclocking right at this very moment just to survive the heat?
Are the transistors fighting a little thermal war inside your computer case? It's very, very likely.
So next time your fan spins up, I want you to think about that giant ZMM register. Think about the giant waking up inside your chip.
That is a great thought. The physical world interacting with the digital world.
Thank you so much for joining us on this very special deep dive. We really hope this slow, detailed explanation helped you visualize the incredible world inside your CPU.
And please don't be afraid of these details. Understanding the hardware makes you a much better programmer.
Absolutely. Keep learning, keep being curious, and we will see you in the next deep dive. Goodbye.
Goodbye.